Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day filled with questions, or perhaps you're the kind of person who finds comfort in stories of human curiosity and discovery rather than counting sheep. Either way, tonight's journey through time is for you. You've got nothing to do but rest. Let your mind wander through the corridors of history, your breathing slow and steady, and your body grow light as if the weight of centuries has lifted from your shoulders. Because tonight, we're traveling back to one of the most extraordinary periods in human history. We're stepping into the 16th and 17th centuries, an era when everything people thought they knew about the universe was turned upside down. When scholars and philosophers began to question ancient wisdom that had stood unchallenged for nearly 2,000 years. When the very methods of seeking truth were reimagined from the ground up. This is the story of the scientific revolution, a transformation so profound that it fundamentally altered not just how we understand the natural world, but how we think about thinking itself. We'll walk alongside the brave minds who dared to look up at the heavens and see them differently, who peered through newly invented lenses and discovered entire worlds invisible to the naked eye, who measured, calculated, and experimented until the universe revealed patterns that had been hidden in plain sight for millennia. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, take a deep breath, settle in, and let's begin our journey into the past. A past where knowledge was being reborn, where courage meant challenging what everyone believed, and where a handful of remarkable individuals lit torches that still illuminate our world today. The world before the revolution. To truly understand the magnitude of what happened during the scientific revolution, we need to first understand the world as it existed before. Close your eyes for a moment and imagine yourself in medieval Europe, perhaps in the year 1400. You're standing in a university town, maybe Bologna or Paris or Oxford. Places where learning flourished even in what we sometimes call the Dark Ages. The streets are narrow and winding, the buildings made of stone and timber. Church bells mark the hours. And in the lecture halls, scholars dressed in dark robes debate the nature of reality itself. But their debates follow very particular rules, and they rely on very particular authorities. The dominant intellectual framework of this era was called the scholasticism, a method of learning that sought to reconcile Christian theology with the philosophical teachings of ancient Greek thinkers, especially Aristotle. Aristotle, who lived in the 4th century before the Common Era, had written extensively about physics, biology, astronomy, logic, and ethics. His works had been lost to Western Europe for centuries, but were rediscovered and translated in the 12th and 13th centuries, largely through contact with the Islamic world where his texts had been preserved and studied. The medieval scholars who studied Aristotle didn't simply read his works as historical documents. They treated them as authoritative truths about how the world actually worked. If Aristotle said something about the nature of motion or the structure of the cosmos, it was accepted as fundamentally correct. The role of the scholar was not to test Aristotle's ideas through observation or experiment, but to understand them more deeply, to reconcile apparent contradictions, and to apply his logical methods to new questions. According to the Aristotelian view that dominated medieval thought, the universe was structured in a very particular way. At the very center of everything was Earth, perfectly still and unmoving. This made intuitive sense to people who could feel solid ground beneath their feet and see the sun, moon, and stars wheeling overhead. Around Earth, a series of crystalline spheres carried the celestial bodies in perfect circular motions. The moon occupied the innermost sphere, then came Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond Saturn lay the sphere of fixed stars, and beyond that, the primum mobile, the outermost sphere that gave motion to all the others, itself moved by divine will. This geocentric, or Earth-centered model had been refined and mathematized by Claudius Ptolemy, a Greco-Roman astronomer who lived in the 2nd century. Ptolemy's system included ingenious mathematical devices called epicycles, small circles whose centers moved along larger circles to account for the apparent backward motion of the planets at certain times. It was complex, but it worked reasonably well for predicting planetary positions, and it aligned perfectly with both common sense observation and religious doctrine. After all, didn't the Bible suggest that God had made Earth as the center of creation, with humanity as the focal point of divine attention? The Aristotelian worldview also made strong distinctions between different types of matter and motion. There was the terrestrial realm, the region below the moon, which was made of 4 elements: earth, water, air, and fire. These elements had natural places they sought to reach. Earth and water naturally moved downward toward the center of the universe, toward the center of Earth itself. Air and fire naturally moved upward. A stone fell because it was made primarily of the earth element and was seeking its natural place. Smoke rose because fire was seeking its natural place in the upper atmosphere. Motion in this terrestrial realm was always either natural, like that falling stone, or violent, meaning it required a continuous force to maintain it. If you pushed a cart and then stopped pushing, the cart would stop moving. This seemed obviously true from everyday experience. Aristotle taught that for an object to keep moving, something had to keep pushing it. There was no concept of what we would now call inertia, the tendency of objects to maintain their state of motion. But the celestial realm, everything above the moon, was fundamentally different. It was made of a 5th element, the quintessence or ether, which was perfect, unchanging, and eternal. The heavens could not decay or alter. Celestial motions were uniform and circular because the circle was the perfect shape, and perfection was the nature of the heavens. There could be no irregularity, no change, no imperfection in that realm. This division between the corrupt, changing terrestrial world and the perfect, unchanging celestial realm was more than just physics. It was theology, philosophy, and cosmology all woven together into a complete worldview. It provided answers to the biggest questions. Where are we? Why are things the way they are? What is our place in the cosmic order? And it did so in a way that seemed to align observation with divine purpose. The methods of learning in this medieval world were also very different from what we would recognize as science today. When scholars wanted to understand a phenomenon, they turned to authoritative texts. They engaged in logical disputation, carefully structured debates following strict rules. They sought to understand the essential nature of things, their formal causes and final purposes. Why does a stone fall? Because its nature is to seek the center. Why do living things grow? Because growth is their inherent purpose, their telos. Observation played a role, certainly, but it was observation guided by theory and interpreted through the lens of authority. If observation seemed to contradict Aristotle or Ptolemy, the assumption was usually that the observation was somehow mistaken or misinterpreted. Not that the ancient authorities might be wrong. After all, these were great minds from antiquity who had thought deeply about these matters. How likely was it that they could all be fundamentally mistaken? There were dissenting voices, of course. Even in the Middle Ages, some thinkers questioned aspects of Aristotelian physics. Scholars in the Islamic world, like Ibn al-Haytham, made important advances in optics and challenged some of Ptolemy's astronomical details. But these remained minority views, refinements around the edges rather than challenges to the core structure of the worldview. As the 15th century gave way to the 16th, this stable intellectual world was about to be shaken to its foundations, not through a single dramatic moment, but through a cascade of questioning, observing, calculating, and daring that would unfold over roughly 2 centuries. The stage was being set for a revolution, though those living through its early days could not have known the magnitude of what was coming. The seeds of change. The scientific revolution didn't emerge from nowhere. It grew from soil that had been quietly enriched by several important developments in the late Middle Ages and Renaissance. These weren't scientific discoveries themselves, but they created the conditions in which revolutionary scientific thinking could take root and flourish. One of the most important of these developments was the Renaissance itself. That great flowering of art, literature, and learning that began in Italy in the 14th century and spread across Europe. Renaissance means rebirth, and it referred to a renewed interest in the literature, art, and learning of classical antiquity. Humanist scholars sought out ancient Greek and Roman texts that had been lost or neglected, translating them, studying them, and in many cases discovering that the ancients had not always agreed with each other. This recovery of diverse ancient sources revealed something important. The classical world had contained multiple competing schools of thought. There were atomists who believed matter was made of tiny, indivisible particles. There were skeptics who doubted the possibility of certain knowledge. There were mathematicians who approached nature through number and geometry. Aristotle's philosophy, for all its comprehensiveness, was not the only game in town in ancient Greece. This diversity of ancient opinion gave Renaissance thinkers permission to question and to compare different ideas. The humanist emphasis on going back to original sources, on reading texts in their original languages rather than through multiple layers of translation and commentary, fostered a more critical attitude toward received wisdom. If the translations and interpretations of Aristotle that had dominated medieval thought sometimes got things wrong, what else might need to be re-examined? What might be discovered by looking at evidence with fresh eyes rather than through the lens of centuries of accumulated commentary? Another crucial development was the invention of the printing press by Johannes Gutenberg around 1450. Before this, every book had to be copied by hand. a laborious process that made books rare and expensive. The printing press changed everything. Suddenly, ideas could spread widely and quickly. A discovery made in Padua could be read in Paris within months. Scientists could publish their findings and share them with colleagues across Europe. Diagrams, tables of data, mathematical proofs could all be reproduced accurately and distributed widely. The printing press also standardized knowledge in important ways. Before printing, each hand-copied manuscript might contain its own errors and variations. With printing, everyone could be working from the same text, seeing the same diagrams, checking each other's calculations. This made collaborative scientific work possible in new ways. It also meant that challenging the consensus view became easier because one could publish one's contrary ideas and have them read by many people. The 15th and 16th centuries also saw dramatic geographic expansion. European explorers ventured into the Atlantic, sailed around Africa to reach Asia by sea, and famously encountered the Americas. These voyages of discovery brought back not just gold and spices, but new plants, animals, and peoples that weren't described in any ancient text. Here were entire continents that Aristotle and Ptolemy knew nothing about. The natural world was clearly more diverse and surprising than the ancients had imagined. This geographic expansion also drove practical needs that encouraged new kinds of knowledge. Navigation across open ocean required better methods of determining latitude and longitude, which meant better astronomical observations and better mathematics. Mapmakers needed to figure out how to represent the curved surface of Earth on flat paper, leading to advances in geometry and projection. Mining operations wanted to pump water out of deeper shafts, creating demand for better understanding of air pressure and mechanics. The Protestant Reformation, beginning with Martin Luther's protests in 1517, shattered the religious unity of Western Europe. While this brought terrible religious wars, it also meant that the Catholic Church's intellectual authority was no longer unquestioned across the continent. In Protestant regions, scholars might feel freer to challenge ideas that had been enforced by Catholic authorities. And, even within Catholic regions, the existence of competing Christian doctrines demonstrated that religious certainty was not as unshakable as it had once seemed. There were also practical traditions of knowledge that existed outside the universities. Craftsmen and artisans, people who worked with their hands, had developed sophisticated techniques for metalworking, glassmaking, and mechanics. These practical workers knew things that weren't written in Aristotle. They knew how to measure carefully, how to tinker and adjust until something worked. As university-trained scholars began to pay more attention to practical crafts and even to get their own hands dirty with experiments, these two traditions began to fertilize each other. Medical schools, particularly those in Italy like Padua, were places where observation mattered in urgent, practical ways. Physicians had to look at actual human bodies, not just read about them. Andreas Vesalius, working in Padua in the early 16th century, produced detailed anatomical drawings based on his own dissections of human cadavers. In doing so, he discovered that some of Galen's descriptions of human anatomy, which had been taken as authoritative for over 1,000 years, were actually based on animal anatomy and didn't always apply to humans. Here was concrete evidence that even the greatest ancient authorities could be wrong about matters of observable fact. All of these threads were coming together: the recovery of diverse ancient sources, the spread of printing, geographic discoveries that exceeded ancient knowledge, practical crafts that valued hands-on experience, religious fragmentation that loosened intellectual authority, and medical observations that showed ancient texts could be mistaken. The time was ripe for someone to look at the heavens and dare to see them in an entirely new way. Copernicus and the Heliocentric Revolution. In 1543, as a Polish church administrator named Nicholas Copernicus lay dying in the town of Frauenburg, a book arrived at his bedside. It was his own book, freshly printed, titled De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. Legend says he regained consciousness long enough to touch this culmination of his life's work before passing away. Whether or not that touching detail is true, the timing was certainly momentous. Copernicus's book would set in motion a revolution that would overturn humanity's understanding of its place in the cosmos. Copernicus had been working on his heliocentric theory, the idea that the Sun, rather than Earth, stood at the center of the universe, for decades. Born in 1473, he had studied mathematics and astronomy, earned a degree in canon law, and served as a church administrator and physician. But his passion was the heavens. Using the astronomical tools and tables available to him, he had studied the motions of the planets and found himself increasingly dissatisfied with the Ptolemaic system. The problem was that while Ptolemy's geocentric model worked reasonably well, it had become increasingly complicated over the centuries as more precise observations revealed discrepancies. Astronomers kept adding more epicycles and adjustments to make the predictions match what they saw in the sky. By Copernicus's time, the system had become an elaborate mathematical contraption. It worked, after a fashion, but it was not elegant. And for Copernicus, who was influenced by Neoplatonic ideas that the universe should be harmonious and beautiful, this lack of elegance was troubling. Copernicus wondered whether there might be a simpler way to account for planetary motions. And he discovered that if you place the Sun at the center instead of Earth, many things became more elegant. The apparent backward motion of planets, which required complicated epicycles in the Ptolemaic system, emerged naturally from a heliocentric model. If both Earth and, say, Mars are orbiting the Sun, then at certain points in their orbits, Earth will overtake Mars. And from Earth's perspective, Mars will appear to move backward against the stars. No epicycles needed, just different planets moving at different speeds around the same central sun. In the Copernican system, Earth became just another planet, the third one out from the Sun. Mercury and Venus orbited closer to the Sun than Earth did, which explained why. These planets were never seen far from the Sun in the sky. Mars, Jupiter, and Saturn orbited farther out. The Moon alone orbited Earth. The stars remained fixed on a distant sphere so far away that Earth's motion around the Sun produced no observable parallax, no apparent shift in stellar positions. This was a radical reimagining of the cosmos. For 2,000 years, educated people had believed Earth stood still at the center of everything. Now, Copernicus was saying that Earth moves, that it races around the sun at tremendous speed and also spins on its axis once per day. This seemed to fly in the face of common sense. If Earth were spinning, why didn't we feel a constant wind? Why didn't objects fly off into space? Why didn't a stone dropped from a tower land far behind as Earth rotated beneath it? Copernicus had answers to these objections, though they weren't entirely satisfying to many readers. He argued that Earth's atmosphere moved with Earth, so we wouldn't feel a wind. He suggested that objects shared Earth's motion, but these explanations required accepting things that couldn't be directly observed and that contradicted Aristotelian physics. More troubling for many was the theological implication. If Earth wasn't the center of the universe, if humanity's home was just one planet among several, what did that mean for religious teachings about humanity's special place in God's creation? Some Bible passages seemed to clearly state that the sun moved around Earth. Hadn't Joshua commanded the sun to stand still, not Earth to stop rotating? The challenge to established cosmology was also a challenge to scriptural interpretation. It's worth noting that Copernicus himself was not trying to undermine religious authority. He was a church official, and he dedicated his book to Pope Paul III. He presented his heliocentric model partly as a mathematical hypothesis, a way of calculating planetary positions that happened to be more elegant than the old way. Whether the heavens were really structured this way was a separate question. This distinction between mathematical models and physical reality gave his work some protection from immediate condemnation. But the implications were clear enough to anyone who thought about it carefully. If the heliocentric model was not just a calculating device but a true description of reality, then the entire Aristotelian cosmology fell apart. There could be no fundamental distinction between terrestrial and celestial realms if Earth was itself one of the celestial wanderers. The crystalline spheres carrying the planets made no sense if planets orbited the sun at different distances. Everything would need to be rethought. At first, Copernicus's ideas spread slowly. His book was technical, written in Latin, and filled with detailed astronomical calculations. It was mainly read by astronomers and mathematicians, many of whom appreciated its mathematical elegance while remaining cautious about accepting it as physically real. Some found middle grounds, like the Tychonic system proposed by Danish astronomer Tycho Brahe, which kept Earth stationary at the center but had the other planets orbit the sun. Yet the seed had been planted. A few bold thinkers began to take the heliocentric model seriously as a description of actual reality. One was Giordano Bruno, an Italian monk and philosopher who in the 1580s went further than Copernicus, arguing that the universe was infinite, filled with countless stars that were themselves suns, potentially with their own planets. Bruno's ideas, combined with his unorthodox theological views, led to his trial for heresy and his execution by burning at the stake in 1600. His fate served as a stark warning about the dangers of challenging established cosmology too boldly. But challenges were coming from another direction as well, not from philosophical speculation, but from careful observation through a revolutionary new instrument that would extend human vision beyond its natural limits. The telescope was about to reveal that the heavens were not at all what Aristotle had described. And the man who would point that telescope skyward and describe what he saw with compelling clarity was an Italian mathematician named Galileo Galilei. Before we turn to Galileo's dramatic discoveries, though, we need to understand another revolution that was happening alongside the astronomical one. This was a revolution in how knowledge itself should be pursued, a reimagining of the very methods by which humans could hope to understand the natural world. And the man who articulated this methodological revolution most clearly was an English philosopher, lawyer, and statesman named Francis Bacon. The method takes shape. Francis Bacon. Francis Bacon was born in 1561 into a family with close connections to Queen Elizabeth's court. His father was Lord Keeper of the Great Seal, and young Francis grew up expecting a career in law and politics. He studied at Cambridge, trained as a lawyer, served in Parliament, and maneuvered through the treacherous waters of court politics. He achieved high office under King James I, rising to become Lord Chancellor. Then, in 1621, his career came crashing down when he was accused and convicted of accepting bribes. He was fined, briefly imprisoned, and permanently barred from holding office. But while Bacon's political career ended in disgrace, his intellectual legacy was just beginning to take shape. Throughout his life, even as he pursued wealth and power, Bacon had been thinking deeply about knowledge. How should we investigate nature? What methods would lead to reliable truths? Why had the natural philosophy inherited from the ancients failed to produce practical benefits for humanity? Bacon's answer was that the old way of doing philosophy was fundamentally flawed. The Aristotelian method of starting with general principles and deducing specific truths might work for mathematics, but it didn't work for understanding nature. Instead, Bacon proposed a radical new approach. Start with careful observations of nature, gather vast quantities of specific facts, and gradually build up to general principles through a process called induction. This was the method he laid out in his most important work, the Novum Organum, published in 1620. The title Novum Organum, Latin for new instrument or new method, was a direct challenge to Aristotle. Aristotle's logical treatises had been called the organon, the instrument. Bacon was declaring that a new instrument was needed for a new age, and he made this challenge explicit on the title page of his book, which showed a ship sailing boldly between the Pillars of Hercules, the ancient markers at the Strait of Gibraltar that represented the boundary of the known world. Below the image was a Latin phrase from the biblical book of Daniel. Many shall pass through, and knowledge shall be increased. Bacon was announcing that humanity was ready to sail beyond the old boundaries of knowledge into uncharted waters. At the heart of Bacon's method was a profound respect for observation and a profound suspicion of the human mind's tendency to jump to conclusions. He recognized that our minds don't passively receive truth from nature. Instead, we actively interpret what we see, and our interpretations are colored by all sorts of biases and preconceptions. Before we can study nature reliably, we need to identify and clear away these distortions. Bacon identified 4 categories of what he called idols, false images that deceive the human mind. The idols of the tribe were biases common to all humans. We tend to see more order and regularity than actually exists. We notice evidence that confirms what we already believe and ignore evidence that contradicts it. We assume that the world works in ways that match our own human nature and experiences. The idols of the cave were individual biases shaped by each person's particular experiences, education, and temperament. One person might be drawn to notice similarities, another to notice differences. One might trust ancient authorities, another might rebel against all tradition. These individual peculiarities distort our perception. The idols of the marketplace arose from language and social interaction. Words often refer to things that don't exist or confuse different concepts under the same name. The way we talk about nature shapes what we think we're observing. Bad definitions and ambiguous terms lead us astray. Finally, the idols of the theater were the false systems of philosophy that had been handed down through history. These were like elaborate stage plays that seemed impressive but didn't reflect reality. Bacon particularly had in mind the philosophical systems of Aristotle and others that relied more on internal logical coherence than on external evidence. Once these idols were recognized and accounted for, the investigator could turn to nature itself with clearer vision. And here Bacon proposed his method. Don't start with grand theories. Start with observations. Gather facts, lots of facts, about the phenomenon you want to understand. But don't just gather random observations. Be systematic. Create tables that organize the information in useful ways. For example, if you want to understand the nature of heat, first make a table of all the instances where heat is present. In fire, in sunlight, in animal bodies, in recently boiled water. Then make a table of instances where heat is absent, in the light of the moon, in will-o'-the-wisps, in the heat of reflection. Then make a table of instances where heat is present in varying degrees. More heat in summer than winter, more heat in boiling water than warm water. By comparing these tables, you can begin to eliminate false hypotheses about what heat really is. If you thought heat must always involve light, the presence of heat in warm water without visible light proves that wrong. If you thought all celestial light involved heat, the coolness of moonlight proves that wrong. Through this process of elimination, called exclusion, you gradually narrow down to the true nature of the phenomenon. This was just the beginning of Bacon's method. From these initial tables, you form tentative hypotheses, what Bacon called the first vintage, an initial harvest of insight. But you don't stop there. You test your hypothesis with new observations, especially looking for what Bacon called prerogative instances, particularly revealing cases that strongly confirm or disconfirm your theory. You refine your understanding step by step, always grounding your conclusions in observed facts. Bacon emphasized that this process should be gradual and cautious. Don't rush to sweeping generalizations. Build your knowledge slowly, testing each step. And crucially, do this work collectively. Science should not be the work of isolated individuals, but of organized communities, sharing observations, comparing results, and building knowledge together. This vision of collective, organized scientific work was most fully expressed in Bacon's utopian fiction, New Atlantis, written shortly before his death and published posthumously in 1626. In this story, sailors discover a hidden island society where an institution called Solomon's House or the College of the 6 Days Works, is devoted entirely to studying nature and applying that knowledge for human benefit. Different groups of researchers have different roles. Some travel the world gathering knowledge from other nations. Some collect information about all sorts of natural phenomena. Some perform experiments. Some analyze results and draw conclusions. This vision of a research institution dedicated to scientific investigation was remarkably prescient. Within a few decades, scientific societies inspired by Bacon's ideas began to form. The Royal Society of London, chartered in 1662, explicitly saw itself as fulfilling Bacon's vision. Its members met regularly to discuss experiments, to witness demonstrations, and to read reports of new discoveries. The Society's motto was nullius in verba, take nobody's word for it, a thoroughly Baconian principle meaning that claims should be tested and verified rather than accepted on authority. Bacon's influence on the scientific revolution was less about specific discoveries and more about this fundamental reorientation of how to pursue knowledge. He wasn't himself much of an experimenter. Many of the scientific details in his works were mistaken. He rejected the Copernican heliocentric theory, perhaps because it seemed too speculative, not grounded enough in what could be directly observed. In that sense, his own work didn't always live up to his methodological ideals. But his core insights were profound and lasting. Nature must be interrogated through observation and experiment, not just contemplated through logic. We must be aware of our biases and actively guard against them. Knowledge should be built gradually from specific facts to general principles, not deduced from assumed first principles. Scientific investigation should be a collective endeavor with shared methods and standards. And the goal of natural philosophy should be practical benefit for humanity, what Bacon called the relief of man's estate. These ideas didn't immediately transform scientific practice, but they seeped into the consciousness of natural philosophers throughout the 17th century. Scientists might not have always followed Bacon's specific procedures, but they absorbed his emphasis on observation, on experimentation, on induction, and on communal verification. The scientific method, as it developed over the following centuries, owed an enormous debt to Francis Bacon's vision. And that method was about to be put to spectacular use. While Bacon was writing about how science should be done, others were actually doing it, training new instruments on the heavens and the hidden world of the very small, and making discoveries that would transform human understanding. Galileo, the telescope and trouble. Galileo Galilei was born in Pisa in 1564, the same year as William Shakespeare. He initially studied medicine, but found his passion in mathematics and natural philosophy. By his mid-20s, he had a position teaching mathematics, first in Pisa, and then at the more prestigious University of Padua. He was brilliant, charismatic, argumentative, and supremely confident in his own reasoning. Even before he turned his telescope to the sky, Galileo had made important contributions to understanding motion. He had studied falling bodies and realized that the Aristotelian idea that heavier objects fall faster than lighter ones was wrong. According to legend, he demonstrated this by dropping objects of different weights from the Leaning Tower of Pisa, though this story is probably apocryphal. What we know he did do was conduct careful experiments rolling balls down inclined planes, measuring how distance increased with time. These experiments led him toward insights about acceleration and inertia that would later influence Newton. But it was the telescope that made Galileo famous and that brought the new astronomy crashing into public consciousness. The telescope itself wasn't Galileo's invention. It had been developed in the Netherlands around 1608 by spectacle makers. Probably Hans Lippershey, who discovered that certain combinations of lenses could make distant objects appear closer. News of this invention spread rapidly, and by 1609, Galileo heard about it. With his mathematical and practical skills, Galileo quickly figured out the optical principles and built his own telescope, then improved it, eventually achieving magnifications of about 20 or 30 times. This might not sound like much by modern standards, but it was enough to reveal things no human had ever seen before. In late 1609 and early 1610, Galileo turned his telescope to the night sky. What he saw astonished him. The moon, rather than being a perfect smooth sphere as Aristotelian cosmology insisted, was rough and mountainous. Galileo could see the shadows cast by lunar mountains and even estimated their heights. The moon was a world with terrain, not so different in character from Earth. The distinction between the perfect celestial realm and the imperfect terrestrial realm was breaking down. The Milky Way, that cloudy band across the sky, resolved into countless individual stars too faint to see with the naked eye. The universe contained far more stars than anyone had imagined, and those stars still appeared as points even through the telescope, suggesting they were incredibly distant, much farther away than the traditional cosmology supposed. Venus showed phases like the moon, cycling from crescent to full and back as it moved in its orbit. This made perfect sense in a heliocentric model where Venus orbited the Sun inside Earth's orbit. It made no sense in the simple geocentric model. Here was direct visual evidence favoring Copernicus. But Galileo's most dramatic discovery came on January 7, 1610. He noticed 3 small stars near Jupiter, arranged in a line. The next night, they had moved. And Jupiter had moved the wrong way relative to them. As he continued to observe over the following nights, Galileo realized these weren't stars at all. They were moons orbiting Jupiter. He eventually identified 4 of them. The large moons we now call Io, Europa, Ganymede, and Callisto. This discovery struck at the heart of a major objection to the Copernican system. Critics had argued that if Earth were moving, it would leave the moon behind. How could the moon keep up with a moving Earth? Galileo's answer was now visible through his telescope. Jupiter was clearly moving through the heavens, yet it didn't leave its moons behind. The moons orbited Jupiter while Jupiter itself moved. By analogy, the moon could orbit Earth while Earth moved around the sun. There was no theoretical impossibility here, only a failure of imagination. In March 1610, Galileo rushed into print with a book describing these discoveries, the Sidereus Nuncius, or Starry Messenger. Written in accessible Latin, filled with engaging descriptions and clear illustrations, it was an immediate sensation. Within weeks, the book had spread across Europe. Here was observational evidence, available to anyone with a telescope, that the heavens were not as tradition described them. Galileo's telescopic discoveries made him famous. He was invited to demonstrate his telescope for princes and cardinals. He was appointed court mathematician to the Grand Duke of Tuscany, a prestigious position that freed him from teaching duties and gave him time for research. For a few years, he was celebrated as a brilliant innovator. But his support for Copernican heliocentrism was increasingly bringing him into conflict with religious authorities. The Catholic Church, dealing with the Protestant Reformation and concerned about challenges to its authority, was not inclined to tolerate attacks on established cosmology, especially attacks that seemed to contradict Scripture. In 1616, the Church officially declared the Copernican theory to be foolish, absurd in philosophy, and formally heretical since it contradicted Holy Scripture. Galileo was warned not to teach or defend heliocentrism as physical fact. He could discuss it as a mathematical hypothesis, but not as truth. For years, Galileo was careful, or relatively careful. But in 1632, he published his masterwork, the dialogue concerning the two chief world systems. Written in Italian rather than Latin, making it accessible to a broader audience, the book was structured as a conversation among three characters debating the Ptolemaic and Copernican systems. One character, Simplicio, defended the old geocentric view and was made to look rather foolish. Another character, Salviati, presented compelling arguments for the Copernican view. The third, Grado, played the intelligent layman, asking questions and eventually being convinced by Salviati's arguments. The dialogue was a brilliant piece of scientific writing, clear, engaging, and persuasive. It was also a barely veiled polemic for heliocentrism. Worse, from the Church's point of view, Galileo had put some of the Pope's own arguments into the mouth of Simplicio, the fool. Whether this was intentional or not, Pope Urban VIII felt insulted and betrayed. Galileo was summoned to Rome and tried by the Inquisition in 1633. Under threat of torture, though probably not actually tortured, the 70-year-old scientist recanted. He formally denied that the sun was the center of the universe or that Earth moved. He was found guilty of vehemently suspected heresy and sentenced to house arrest for the remainder of his life. The story, perhaps apocryphal, is that after his recantation, Galileo muttered under his breath, "Eppur si muove," and yet it moves. Whether he said it or not, it captures the essential truth. The evidence was there. Earth does move. The old cosmology was wrong. And no amount of authority or intimidation could make the observations disappear. Galileo spent his final years under house arrest, his health failing, eventually going blind. But even in this confinement, he continued to work. He wrote the discourses concerning two new sciences, a more technical book about mechanics, motion, and the strength of materials. This work, smuggled out and published in the Netherlands in 1638, would be important for Newton's later development of physics. Galileo died in 1642, the same year that Isaac Newton was born, a symbolic passing of the torch. His trial had a chilling effect on scientific work in Catholic countries, but it couldn't stop the spread of the new ideas. Too many people had looked through telescopes. Too much evidence had accumulated. and other brilliant minds were pushing the revolution forward in different directions. Kepler and the mathematics of the heavens. While Galileo was making his telescopic discoveries, a German astronomer and mathematician named Johannes Kepler was pursuing his own vision of the heavens. Kepler's path to his revolutionary discoveries about planetary motion was winding and marked by both brilliant insights and some rather strange mystical beliefs. He somehow managed to combine rigorous mathematical work with a conviction that numerical harmonies held the secret to God's design of the cosmos. Kepler was born in 1571 in the Holy Roman Empire, in what is now Germany. His childhood was difficult. His father abandoned the family, and Johannes suffered from smallpox as a child, which left his hands crippled and his vision permanently impaired. But he was brilliant at mathematics, and he earned a scholarship to study for the Lutheran ministry. His studies included astronomy, and he showed such talent that when a post teaching mathematics opened up in Graz, Austria, he was recommended for it despite not yet finishing his theological studies. In Graz, Kepler became fascinated with the Copernican system. He wondered why there were exactly 6 planets, no more, no fewer, and why they orbited at the particular distances they did from the Sun. In 1596, he published a book proposing an answer. Kepler imagined the 6 planets' orbits as being defined by spheres nested between the 5 Platonic solids, the perfect 3-dimensional geometric shapes. It was an elegant idea, combining geometry with astronomy. It was also wrong, but it demonstrated Kepler's mathematical creativity and brought him to the attention of Tycho Brahe. Tycho Brahe was the greatest observational astronomer before the telescope. Working from his observatory on an island near Copenhagen, Tycho had spent decades making extraordinarily precise measurements of planetary positions using huge, carefully calibrated instruments. His observations were far more accurate than anything done before. But Tycho wasn't a Copernican. He had developed his own compromise system, with Earth stationary at the center, the Sun orbiting Earth, and the other planets orbiting the Sun. In 1600, Tycho moved to Prague to serve as imperial mathematician to the Holy Roman Emperor. He needed a talented assistant to help analyze his massive collection of observations, and he hired Kepler for the job. The collaboration was tense. Tycho was proprietary about his data, and Kepler was impatient. But when Tycho died suddenly in 1601, Kepler inherited his position and, more importantly, gained access to all those precious observations. Kepler set out to analyze the orbit of Mars using Tycho's data. Mars was particularly important because its orbit is markedly elliptical, though no one knew that yet. For years, Kepler tried to fit Mars's observed positions to a circular orbit, adding small corrections and adjustments. Nothing worked. The observations simply wouldn't match a perfect circle, even allowing for epicycles and other geometric tricks. After immense labor, filling hundreds of pages with calculations, Kepler made a radical decision. What if planetary orbits weren't circular? Circles were the perfect shape, and the heavens were supposed to be the realm of perfection. But the data was telling him something different. What if planets moved in ellipses, ovals, with the Sun at one focus of the ellipse rather than at the center? This was the insight that became Kepler's first law of planetary motion. Planets move in elliptical orbits with the Sun at one focus. It was published in his book Astronomia Nova, The New Astronomy, in 1609, a monumentally important work that represented years of painstaking calculation. But Kepler didn't stop there. He noticed another pattern in the data. A planet moves faster when it's closer to the Sun and slower when it's farther away. But the relationship wasn't arbitrary. Kepler discovered that if you draw a line from the Sun to the planet, that line sweeps out equal areas in equal times. When the planet is close to the Sun, it moves faster and covers more distance along its orbit. But the triangular slice defined by the Sun, the starting point and the ending point, has the same area as when the planet is farther out, moving slower and covering less distance. This became his second law, the law of equal areas. These first two laws, published in Astronomia Nova, demolished the ancient insistence on perfect circular motion. They also provided a way to calculate planetary positions far more accurately than any previous system, whether Ptolemaic or even earlier versions of Copernican astronomy. The universe, it turned out, preferred ellipses to circles. Kepler continued to search for mathematical harmonies. He was convinced that God had designed the cosmos according to beautiful mathematical principles, and that discovering these principles was a form of thinking God's thoughts after him. In 1619, he published Harmonic Mundi, The Harmony of the World, in which he announced his third law of planetary motion. This law related each planet's orbital period, the time it takes to complete one orbit, to its distance from the Sun. Specifically, Kepler found that the square of the orbital period was proportional to the cube of the average distance from the Sun. If you knew how far a planet was from the Sun, you could calculate how long its year was, and vice versa. This mathematical relationship linked all the planets together in a unified system. Kepler's three laws were revolutionary. They showed that the motions of the planets could be described with elegant mathematical precision without resorting to the Baroque complications of epicycles and crystalline spheres. They were compatible with a heliocentric system and essentially incompatible with a geocentric one. They provided concrete, testable predictions. But there was something missing. Kepler's laws described how the planets moved, but not why. What force or principle caused planets to move in these particular elliptical paths? Kepler speculated about some sort of magnetic influence emanating from the Sun, pushing the planets along their orbits, but he couldn't work out the details. That explanation would have to wait for Newton. Kepler's work was also remarkable for its methodological approach. Like Bacon, though working independently, Kepler emphasized the importance of careful observation and the need for theories to match empirical data. When circular orbits didn't fit Tycho's observations, Kepler didn't adjust the observations or make excuses. He changed his theory. The universe was what it was, not what human aesthetics or inherited philosophy said it should be. His calculations were extraordinarily laborious. This was decades before calculus, before logarithms were widely known, before calculating machines. Kepler did it all by hand, arithmetic and geometry, page after page, often having to redo calculations when he found an error. The sheer determination and rigor he brought to the work was staggering. Kepler also faced personal hardships throughout his life. His first wife died. His son died. His mother was tried for witchcraft, and Kepler had to work hard to defend her. He struggled with poor eyesight and poor health. The 30 Years' War disrupted his life and work. Yet through it all, he continued his calculations, driven by a deep faith that mathematical order underlay the cosmos and that human minds could grasp it. By the time of Kepler's death in 1630, the pieces of the new astronomy were in place. The Sun was at the center. Earth and the other planets moved in elliptical orbits according to precise mathematical laws. The heavens were not perfect and unchanging, but followed natural principles that could be observed and calculated. What was still needed was a comprehensive framework that would explain not just how planets moved, but why. That framework would eventually come from Isaac Newton. But before we reach Newton's grand synthesis, we need to consider another thinker who approached the revolution from the direction of philosophy and mathematics: René Descartes. Descartes and the Power of Reason. René Descartes, born in France in 1596, came of age in a world being transformed by the new science. He was educated by Jesuits, receiving a traditional scholastic education in philosophy and theology. But he quickly became dissatisfied with the uncertainty and disagreement that seemed to characterize all philosophical questions. Where Galileo and Kepler looked to observation and calculation to ground truth, Descartes looked inward to the mind itself. Descartes' most famous contribution to philosophy came through his radical method of doubt. He decided to doubt everything that could possibly be doubted, to strip away all beliefs that weren't absolutely certain, and then to rebuild knowledge on an unshakable foundation. He could doubt his senses, since they sometimes deceive. He could even doubt that the physical world exists, since he might be dreaming. But one thing he couldn't doubt was that he was doubting. The very act of thinking proved that he, as a thinking being, existed. This gave him his most famous philosophical principle: cogito, ergo sum, I think, therefore I am. From this foundation of the thinking self, Descartes tried to rebuild knowledge. He argued that clear and distinct ideas perceived by the mind must be true. He thought he could prove God's existence through pure reason. And, crucially for science, he believed that the physical world could be understood entirely through mathematics and mechanics. Descartes envisioned the universe as a kind of vast machine. Matter extended through space, and all of nature could be explained through the motion of this matter according to mechanical laws. There were no hidden purposes, no final causes in Aristotle's sense. Things happened because of efficient causes, one physical thing pushing or pulling another. The universe was like clockwork, operating by fixed rules. This mechanical philosophy, as it came to be called, was enormously influential. It offered a way to think about nature that was very different from the Aristotelian emphasis on forms and purposes. You didn't need to ask why a stone falls in the sense of what purpose the fall serves. You just needed to understand the mechanical causes, the forces and motions involved. Descartes made concrete contributions to science as well as to philosophy. In mathematics, His most important innovation was the development of analytic geometry, the method of describing geometric shapes using algebraic equations. By setting up coordinate axes, what we now call Cartesian coordinates, in his honor, Descartes could represent a curve as an equation. A circle, for instance, could be described by the equation x squared plus y squared equals r squared. This might seem like a minor technical advance, but it was revolutionary. It unified geometry and algebra, showing that geometric problems could be solved using algebraic techniques and vice versa. It also laid groundwork for calculus, which Newton and Leibniz would develop later in the century. The ability to describe motion mathematically, to represent changing quantities with equations, would be essential for the new physics. Descartes also worked on optics, investigating how light bends when it passes from one medium to another. He correctly derived the law of refraction, though not with a complete understanding of what light actually is. His work on optics was part of a broader mechanistic explanation of light as a kind of pressure transmitted through a medium. In cosmology, Descartes proposed a theory of vortices. He imagined space filled with subtle matter that swirled in vast whirlpools. The planets were carried around the sun by the swirling motion of these vortices. This was an attempt to provide a mechanical explanation for planetary motion, an alternative to Kepler's speculations about magnetic forces. It was an elegant idea, but it turned out to be wrong. Newton's theory of gravity would eventually replace it. Yet even though some of Descartes' specific scientific theories didn't pan out, his broader influence was profound. His emphasis on mathematics as the language of nature, his mechanical philosophy, his systematic doubt, and his insistence that reason could unlock the secrets of the universe all shaped how scientists thought about their work. Descartes also exemplified a new kind of intellectual figure. He wasn't primarily a university professor teaching Aristotle to students. He was an independent scholar, communicating through published books and correspondence with other leading thinkers across Europe. This network of correspondence, facilitated by the printing press and by gradually improving postal systems, created an international community of natural philosophers who could share ideas, debate theories, and build on each other's work. The mechanical philosophy that Descartes championed became one of the dominant frameworks of 17th century science. Thinkers across Europe adopted the view that nature operated like a machine, governed by deterministic laws. This view had theological implications. If the universe was a machine, then God was the great mechanic who had designed and built it, set it running according to fixed laws, and now perhaps stood back and let it operate. This deist view, as it came to be called, was compatible with Christianity, but represented a shift away from the more interventionist God of medieval theology. Not everyone accepted the mechanical philosophy completely. Some phenomena, especially those involving life and consciousness, seemed resistant to purely mechanical explanation. How could a machine think? How could matter feel? These questions would trouble philosophers for centuries and remain unresolved in many ways even today. But for the physical sciences, for understanding the motion of planets and projectiles, the behavior of gases and liquids, the nature of light and sound, the mechanical philosophy proved remarkably powerful, and it would reach its fullest expression in the work of Isaac Newton, whose synthesis of mathematics, observation, and mechanical reasoning would create a comprehensive new physics. Newton, the grand synthesis. Isaac Newton was born on Christmas Day in 1642 by the old calendar, the year Galileo died. His father had died before his birth, and his mother remarried when Isaac was 3, leaving him to be raised by his grandmother. It was not a happy childhood. Newton grew up introverted, deeply intelligent, and prone to holding grudges. He showed mechanical aptitude as a boy, building models and sundials, but seemed destined for life as a farmer until an uncle recognized his intellectual gifts and arranged for him to attend Cambridge University. Newton arrived at Cambridge in 1661, where he was supposed to study Aristotle, but instead began reading the new philosophy: Descartes, Galileo, Kepler, Boyle. In 1665, plague swept through England, and Cambridge University closed. Newton returned home to Woolsthorpe, to the family farm, for what would become the most productive extended period of scientific thought in history. Over the next 18 months, sometimes called Newton's Annus Mirabilis, his year of wonders, though it actually lasted longer than a year, the 20-something Newton made astonishing advances in 3 major areas: mathematics, optics, and mechanics. In mathematics, Newton invented calculus, or, as he called it, the method of fluxions. Calculus is the mathematics of change, of quantities that vary continuously. It provides tools for calculating instantaneous rates of change, like how fast a falling object is moving at a particular instant, and for calculating areas and volumes of curved shapes. Newton didn't publish his calculus work immediately, which later led to a bitter priority dispute with German mathematician Gottfried Wilhelm Leibniz, who independently invented calculus around the same time and published first. Both deserve credit for this revolutionary mathematical tool, though their notations were different, and it was Leibniz's notation that eventually became standard. In optics, Newton conducted a series of experiments with prisms. He discovered that white light was not simple and pure, as people had thought, but was composed of a mixture of different colors. When white sunlight passed through a prism, it spread out into a spectrum of colors, what Newton called the prismatic colors. And, crucially, when he passed the separated colors through a second prism, they didn't change or spread further. Red light stayed red, blue stayed blue. The colors were fundamental components of white light, not created by the prism. This discovery overturned centuries of thinking about color and light. It also led Newton to design a new kind of telescope. Traditional telescopes used lenses, but lenses caused chromatic aberration, rainbow-colored fringes around images because different colors refract through lenses at slightly different angles. Newton realized that mirrors would reflect all colors equally, so he built a reflecting telescope. It worked brilliantly and brought him to the attention of the Royal Society. But Newton's most important work during this period was in mechanics. He was thinking about motion, about force, about what kept the moon in orbit around Earth and the planets in orbit around the sun. And he made a daring conceptual leap. The same force that pulls an apple to the ground also reaches across space to hold the moon in its orbit. This wasn't an original thought in the sense that others had wondered about it, but Newton had the mathematics to actually calculate it. Using his new calculus and Kepler's laws, Newton worked out that if gravity followed an inverse square law, meaning the force decreased with the square of the distance, then you could explain both falling apples and orbiting moons. Newton didn't immediately publish this work. He was cautious, perhaps perfectionistic. He also got embroiled in disputes and became reluctant to share his ideas for fear of criticism. But in 1684, the astronomer Edmund Halley visited Newton and asked him a question. What curve would a planet follow if it was attracted to the sun by a force that decreased as the square of the distance? Newton replied immediately, an ellipse. He had already worked it out years ago. Halley was astounded and begged Newton to write it up. Under Halley's encouragement and with Halley's financial backing for publication, Newton spent 2 intense years expanding his calculations and arguments into a complete work. The result was published in 1687. Philosophiae Naturalis Principia Mathematica. Mathematical Principles of Natural Philosophy, known ever since simply as the Principia. The Principia is one of the most important scientific books ever written. In it, Newton laid out 3 laws of motion that apply to all objects everywhere. The first law: an object in motion stays in motion with the same speed and direction unless acted upon by an external force. This is the principle of inertia that Galileo had glimpsed and Descartes had articulated. An object at rest stays at rest unless forced to move. There's no need for a force to maintain motion, only to change it. The second law: force equals mass times acceleration. This quantitative relationship allowed Newton to calculate exactly how objects would move under various forces. If you knew the forces acting on an object, you could predict its motion with mathematical precision. The third law: for every action, there is an equal and opposite reaction. When you push on something, it pushes back on you with equal force in the opposite direction. This explained a range of phenomena, from why guns recoil when fired to how birds fly. These 3 laws, combined with Newton's law of universal gravitation, provided a complete framework for understanding motion. The law of universal gravitation stated that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, F equals G times m1 times m2 divided by r squared, where G is a universal constant. With this simple equation and the 3 laws of motion, Newton could explain and predict an enormous range of phenomena. Why planets move in elliptical orbits? Because gravity provides exactly the right force to keep them in that path. Why the moon doesn't fly away from Earth or crash into it? Because its orbital motion and gravity balance perfectly. Why tides rise and fall? Because the moon's gravity pulls on Earth's oceans. Why comets follow long elliptical paths? Because they too are governed by the sun's gravity. Why a cannonball follows a parabolic curve? Because Earth's gravity pulls it down, while its forward momentum carries it ahead. The Principia also demonstrated that the same laws governed both terrestrial and celestial phenomena. There was no fundamental distinction between the physics of falling apples and the physics of orbiting planets. This unified heaven and earth in a way that completely demolished what remained of the Aristotelian distinction between the two realms. Newton's work was rigorous, mathematical, and comprehensive. He proved his results geometrically, using the mathematical style that educated readers of his time would expect. He showed that his laws could explain not just the idealizations, but also the small deviations and perturbations that astronomers had observed. He worked out why the moon's orbit wobbles slightly, because the sun's gravity tugs on the moon, as well as Earth's gravity. He explained the precession of the equinoxes, a slow shift in the Earth's rotational axis, as resulting from the gravitational pull of the sun and moon on Earth's equatorial bulge. It was, in short, a triumph of scientific reasoning, and it established a model for what science should look like: mathematically rigorous, empirically grounded, comprehensive in scope, and capable of making precise predictions that could be tested against observation. Newton's influence extended beyond the specific content of the Principia. His work demonstrated that the universe operated according to rational, discoverable laws. It showed that nature was fundamentally mathematical, and it suggested that human reason, properly applied, could unlock the deepest secrets of how things worked. These ideas would resonate through the Enlightenment and shape Western thought for centuries. Yet Newton himself was a more complex figure than the portrait of the cool, rational scientist might suggest. He spent as much time on alchemy and biblical chronology as on physics. He had a mystical streak, and saw his work on gravity as revealing God's design. He was secretive, suspicious of criticism, and capable of vicious attacks on intellectual rivals. His dispute with Leibniz over credit for calculus was particularly ugly, with Newton using his position as a president of the Royal Society to ensure that official investigations sided with him. Newton also didn't explain everything. He admitted that he didn't know what gravity actually was or how it acted across empty space without any physical contact. His famous phrase was hypotheses non fingo. I do not feign hypotheses. He could describe how gravity worked mathematically and predict its effects with precision, but he wouldn't speculate about its underlying mechanism. This bothered some of his contemporaries, who thought it sounded too much like occult action at a distance. But Newton insisted that the mathematics worked, and the predictions matched observation, and that was enough. After the Principia, Newton largely withdrew from intensive scientific work. He became involved in university politics at Cambridge, then accepted a position at the Royal Mint in London, where he zealously pursued counterfeiters. He was elected president of the Royal Society and used that position to dominate English scientific life, not always graciously. He was knighted in 1705, the first scientist to receive such an honor for scientific achievements. When he died in 1787, he was buried in Westminster Abbey with honors befitting a national hero. By the time of Newton's death, the scientific revolution was essentially complete in its initial phase. The old Aristotelian worldview had been replaced by a mechanistic, mathematical understanding of nature. The scientific method, grounding claims in observation and experiment, had become established practice among natural philosophers. And institutions like the Royal Society provided venues for scientists to share their work and build on each other's discoveries. The instrument makers. While brilliant theorists like Galileo, Kepler, and Newton were revolutionizing how we understand the universe, another quiet revolution was happening in workshops and laboratories. This was the revolution of scientific instruments, the tools that extended human senses and made new kinds of observations possible. Without these instruments, many of the discoveries of the scientific revolution simply couldn't have happened. We've already encountered the telescope, perhaps the most famous scientific instrument of the era. But its development involved more than just Galileo. Telescope design improved rapidly through the 17th century as opticians learned to grind better lenses and construct more stable mounts. The reflecting telescope that Newton invented solved the problem of chromatic aberration and allowed for even more powerful magnification. By the late 17th century, astronomers were using telescopes that revealed increasingly fine details of the moon, the phases of Venus, the moons of Jupiter, and more. But there was another optical instrument that proved equally revolutionary for exploring nature: the microscope. Like the telescope, the compound microscope, which used multiple lenses to achieve high magnification, was invented in the Netherlands, probably in the 1590s by spectacle makers Zacharias and Hans Janssen. Early microscopes were crude and produced distorted images, but they opened up an entirely new realm for exploration: the very small. By the mid-17th century, microscopes had improved significantly, and natural philosophers began to systematically examine the miniature world. Robert Hooke, an English scientist and brilliant instrument maker, published Micrographia in 1665, a lavishly illustrated book depicting what he saw through his microscope. He examined the structure of cork and described how it was made of tiny compartments that he called cells, the first use of that term in biology. He illustrated the compound eyes of insects in stunning detail. He showed the intricate structures of feathers, the crystalline forms of frost, the fine hairs on leaves. Hooke's Micrographia was a sensation. It demonstrated that an entire hidden universe existed below the threshold of normal vision, a universe of complexity and beauty that raised profound questions. If such order and intricacy existed in things so small we couldn't see them, what might that say about the nature of creation? Even more remarkable observations came from Antony van Leeuwenhoek, a Dutch tradesman with no scientific training, but with exceptional skill at grinding tiny, nearly spherical lenses. Leeuwenhoek's simple microscopes, really just single powerful lenses, achieved magnifications of up to 270 times, better than most compound microscopes of the era. And what he saw astonished the world. Leeuwenhoek examined drops of water from ponds, canals, and rain barrels. In these drops, he saw countless tiny creatures swimming about, creatures far too small to see with the naked eye. He called them animalcules. Today, we call them microorganisms. Leeuwenhoek had discovered bacteria, protozoa, and other microscopic life. He examined blood and saw red blood cells. He looked at his own dental plaque and found it teeming with living things. He observed muscle fibers, nerve fibers, and the structure of plant tissues. For the rest of his long life, Leeuwenhoek sent letters describing his observations to the Royal Society in London, which published them in their journal. He never traveled to England himself, never learned Latin, and worked alone in the Dutch city of Delft. But his careful observations opened up microbiology and laid groundwork for understanding that life existed at scales far beyond what anyone had imagined. Other instruments were being developed for other purposes. The thermometer, which measures temperature, went through several iterations in the 17th century. Galileo built an early version, really a thermoscope, in which the expansion and contraction of air moved water in a tube. Later versions used alcohol or mercury in sealed tubes with standardized scales. Precise thermometers allowed scientists to study heat quantitatively rather than just qualitatively. The barometer, which measures air pressure, was invented by Evangelista Torricelli, one of Galileo's students, in 1643. Torricelli filled a tube with mercury, inverted it in a dish of mercury, and watched as the mercury in the tube fell to a certain height, leaving a vacuum at the top. The height of the mercury column was supported by the pressure of the atmosphere pushing on the mercury in the dish. This simple device proved that air had weight and pressure. Subsequent experiments showed that air pressure varied with altitude and weather, opening up new areas of study. Robert Boyle, working in Oxford in the 1660s with assistance from Robert Hooke, developed an air pump that could create partial vacuums. With this device, Boyle conducted experiments showing that sound couldn't travel in a vacuum, that candles couldn't burn without air, and that animals couldn't survive without air. He also investigated the relationship between the pressure and volume of air, discovering what came to be called Boyle's law. For a fixed amount of gas at constant temperature, pressure and volume are inversely related. These investigations of air and vacuum challenged Aristotelian ideas about nature abhorring a vacuum. They showed that empty space could exist and that air was a material substance with measurable properties. This fit well with the mechanical philosophy's view of nature as matter in motion. Clocks became more precise during this period as well, which was crucial for many scientific observations. Christiaan Huygens, a Dutch scientist, invented the pendulum clock in 1656, based on Galileo's observation that pendulums swing with regular periods. Accurate clocks allowed for precise timing of astronomical events, which was necessary for determining longitude at sea and for making detailed observations of planetary motions. All of these instruments shared something in common. They extended human capabilities. Telescopes and microscopes extended vision. Thermometers and barometers quantified sensations like hot and cold or heavy and light air. Clocks precisely measured time. Balances and scales precisely measured mass. Each instrument opened new domains for investigation and made possible observations that unaided human senses couldn't achieve. Importantly, these instruments also required craftsmanship and practical skill. The best microscope lenses had to be ground and polished to precise specifications. Telescopes needed carefully calibrated supports. Barometers had to be constructed with clean mercury and vacuum-sealed tubes. Science was becoming a hands-on enterprise requiring not just mathematical and theoretical insight, but also experimental apparatus and technical expertise. This practical, experimental dimension of the scientific revolution was exemplified by the Royal Society of London, which from its founding in 1662 emphasized public demonstrations of experiments. Members would gather to witness experiments performed with these new instruments. Robert Hooke, as curator of experiments, was responsible for demonstrating new phenomena at each meeting. The idea was that scientific claims should be witnessed and verified, not just taken on authority. Seeing was believing. This culture of experimentation and instrumental observation spread across Europe. Academies of science were founded in Paris, Berlin, and other cities. Scientific journals published descriptions of experiments and instruments, allowing scientists in different countries to replicate and verify each other's work. The printing press, once again, was crucial here, allowing technical diagrams and descriptions to be widely shared. The instruments developed during the scientific revolution weren't just tools for making isolated discoveries. They fundamentally changed how science was done. They made science more empirical, more quantitative, and more replicable. They democratized scientific observation in a sense because anyone with access to a telescope or microscope could see the moons of Jupiter or the cells in cork. Science was becoming less about contemplating philosophical principles and more about looking, measuring, and experimenting. The life sciences transform. While the astronomical and physical sciences were undergoing dramatic transformations, equally profound changes were happening in the study of living things. The old texts of Galen and other ancient medical authorities which had dominated medical education for over 1,000 years were being challenged by careful observation and dissection. Andreas Vesalius, born in 1514 in Brussels, represents the beginning of modern anatomy. Educated at the University of Padua, which had the most advanced medical school in Europe, Vesalius was passionate about understanding the human body by direct observation rather than by reading ancient texts. In his time, it was still common for anatomy professors to sit in a chair reading from Galen, while a surgeon performed the actual dissection on a cadaver below. Vesalius changed this. He performed dissections himself, carefully examining each structure, each muscle, each bone, each organ. In 1543, the same year Copernicus published his heliocentric theory, Vesalius published De Humani Corporis Fabrica, on the fabric of the human body. This massive work contained detailed, accurate illustrations of human anatomy based on Vesalius's own dissections. The illustrations were beautiful and precise, showing muscles, bones, blood vessels, and organs in exquisite detail. They were far superior to anything that had come before. More importantly, Vesalius pointed out numerous errors in Galen's descriptions. Galen had based much of his anatomy on dissections of animals, particularly dogs and Barbary apes, assuming that human anatomy was essentially the same. It wasn't. Vesalius showed that the human jawbone was in one piece, not two, as Galen had described. He showed that the human liver had 2 lobes, not 5. He challenged Galen's description of how blood moved through the heart. This willingness to contradict ancient authority based on direct observation was a hallmark of the new scientific approach. Vesalius's work established anatomy as a discipline grounded in careful dissection and observation. Medical students after Vesalius would learn by looking at actual human bodies, not just by reading texts. The next major breakthrough in medicine came from understanding how blood moved through the body. The ancient view, inherited from Galen, was that blood was continuously created in the liver, moved outward through the veins to be consumed by the body's tissues, and then was replenished by eating more food. It was a one-way system of production and consumption, not a circulatory system. William Harvey, an English physician educated at Padua, questioned this view. Through careful experiments and observations, he showed that blood actually circulates. The heart acts as a pump, pushing blood out through arteries to all parts of the body. The blood then returns through veins back to the heart. It's a closed loop, with the same blood moving round and round. Harvey published his findings in 1628 in a book called De Motu Cordis, on the motion of the heart. His evidence was compelling. He calculated how much blood the heart pumped with each beat. If blood were being consumed as Galen thought, the liver would have to produce an impossibly large amount of blood every hour. But if blood circulated, returning to the heart to be pumped again, the system made sense. Harvey also demonstrated the one-way valves in veins that prevented blood from flowing backward. He showed through experiments on living animals how blocking an artery stopped blood flow beyond that point, while blocking a vein caused blood to pool on the side closer to the heart. All of this pointed to circulation. Harvey's work was initially controversial, but eventually it was accepted. It represented a fundamental revision of how the body worked, and it aligned with the mechanical philosophy. The body was being understood as a kind of hydraulic machine, with the heart as a pump and blood vessels as pipes. The discovery of capillaries, the tiny blood vessels that connect arteries to veins, came a few decades later. Marcello Malpighi, using the microscope, observed capillaries in the lungs of frogs in 1661. This filled in the missing link in Harvey's circulation system. Blood moved from the heart through ever smaller arteries, through microscopic capillaries where it exchanged oxygen and nutrients with tissues, and then back through ever larger veins to the heart. The microscope revealed other aspects of biology as well. Leeuwenhoek's observations of sperm cells, blood cells, and bacteria opened up entirely new questions about reproduction, disease, and the nature of life itself. If tiny organisms existed everywhere, invisible to the naked eye, what role did they play in nature? Could they be related to disease? These questions wouldn't be fully answered until the germ theory of disease in the 19th century, but the scientific revolution planted the seeds. Plant anatomy also advanced. Scientists used microscopes to study the structure of plant tissues, observing cells, vascular structures, and the intricate patterns of growth. They conducted experiments on plant physiology, investigating how plants took in water, how they reproduced, how they responded to light. Classification of living things became more systematic. Naturalists cataloged the diversity of life, describing new species brought back from voyages of exploration. The sheer variety of life on Earth was becoming apparent, and scientists began to seek principles for organizing this diversity. In all of these life sciences, the same pattern emerged. Careful observation trumped ancient authority. Instruments like the microscope revealed previously hidden structures, and experimentation provided insights into function and mechanism. The body and all of life were being understood not through mystical vital forces, but through structure and mechanism in ways that paralleled how the physical world was being understood through Newton's mechanics. The legacy and lasting impact. As the 17th century drew to a close, the intellectual landscape of Europe had been transformed beyond recognition. The cosmos that the ancient Greeks had described, with its crystal spheres and natural places, had been replaced by a vast, perhaps infinite space, governed by universal mathematical laws. The idea that the same principles applied in the heavens and on Earth, that a falling apple and an orbiting moon followed the same law of gravitation, unified the universe in a way that would have been unthinkable just 2 centuries earlier. The methods of gaining knowledge had shifted fundamentally. Authority, whether Aristotle or Scripture, no longer had the final word on questions about the natural world. Direct observation, controlled experiment, mathematical analysis, and reproducible demonstration had become the standards for scientific truth. Francis Bacon's vision of systematic empirical investigation and collective scientific work was being realized in scientific societies and journals across Europe. The mechanical philosophy, the view that nature operated like a vast machine according to fixed laws, had become the dominant framework for understanding the physical world. This didn't necessarily deny divine creation. Many of the key figures of the scientific revolution were deeply religious, but it changed how God's relationship to nature was conceived. God became the great designer, the cosmic clockmaker, who had set up the laws and initial conditions, and now let the machine run. This had profound implications beyond science. If the natural world operated by rational, discoverable laws, might not human society and politics also be governed by natural laws? The Enlightenment of the 18th century would take this idea and run with it, applying reason and systematic investigation not just to nature, but to society, government, economics, and ethics. The spirit of questioning authority, of demanding evidence, of believing in progress through application of reason, all of these were legacies of the scientific revolution. The practical impacts were significant as well. Newton's mechanics would eventually enable the Industrial Revolution, as engineers applied mathematical understanding of forces and motion to build better machines. The emphasis on experimentation and observation led to improvements in agriculture, medicine, and technology. Knowledge was increasingly seen not just as valuable for its own sake, but for its practical benefits, for improving the human condition, just as Bacon had urged. Scientific institutions became permanent features of European society. Universities gradually reformed their curricula to include the new science. Academies and societies provided venues for scientific discussion and publication. Scientific careers became possible for talented individuals, though still limited mainly to those with independent means or with wealthy patrons. The scientific revolution also created a new kind of cultural hero. Newton, in particular, became an icon, celebrated not just for his discoveries, but as the embodiment of human reason's power to understand nature. The poet Alexander Pope captured this sentiment in a famous couplet. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Yet, it's important to recognize what the scientific revolution did not accomplish. It was primarily a European phenomenon, centered in Western Europe, though with important contributions from places like Poland and Bohemia. It had little impact on most people's daily lives in the 17th and 18th centuries. It focused mainly on physics and astronomy, with some progress in anatomy and medicine, but biology, chemistry, and earth sciences would not fully undergo their own revolutions until the 18th and 19th centuries. Many questions remained unanswered. What was light? Was it particles or waves? Newton and others debated this without resolution. What was heat? How did electricity work? These questions would occupy scientists in the following centuries. The nature of life, consciousness, and reproduction remained deeply mysterious. Chemistry still awaited a systematic framework. There were also troubling aspects to how the new science developed. The increasing mathematization and mechanization of nature could seem cold and reductionist, draining the world of the meaning and purpose. The philosopher Blaise Pascal expressed this anxiety. The eternal silence of these infinite spaces frightens me. If we're just matter in motion, governed by blind mechanical laws, what becomes of human significance, of free will, of moral purpose? Women were largely excluded from the formal institutions of science during this period, though some made important contributions despite the barriers. Margaret Cavendish wrote extensively on natural philosophy, though her work was often dismissed. Maria Sibylla Merian made detailed studies of insect metamorphosis. Émilie du Châtelet translated Newton's Principia into French. But these were exceptions. The scientific community, like the universities and learned societies, was overwhelmingly male, and the relationship between science and religion remained complex and sometimes fraught. Galileo's trial demonstrated that challenging traditional cosmology could be dangerous. Yet many scientists saw no conflict between their faith and their investigations of nature. They believed that studying nature was a way of appreciating God's creation, reading the book of nature alongside the Bible. Despite these qualifications and complications, the significance of the scientific revolution is undeniable. It marked a fundamental shift in how humans understood their place in the universe and how they approached the quest for knowledge. It laid the foundations for all of modern science. The methods established then, the emphasis on observation, experiment, measurement, and mathematical description, remain at the heart of scientific practice today. We live in a world built on the insights of the scientific revolution. When we launch satellites into orbit, we use Newton's laws and Kepler's laws. When we develop new medicines, we rely on understanding of human anatomy and physiology that traces back to Vesalius and Harvey. When we build computers and smartphones, we use mathematics that includes Descartes' coordinate geometry. When we seek to understand anything in nature, we follow the empirical methods that Bacon articulated. And, perhaps most fundamentally, we inherit from the scientific revolution the conviction that the universe is knowable, that human reason and observation can penetrate nature's secrets, that progress in understanding is possible. These ideas are so deeply embedded in modern culture that it's easy to forget how revolutionary they once were. Now, as your thoughts begin to drift and the boundaries between waking and sleeping blur, consider this. You are part of that continuing story of discovery. Every time you question an assumption, every time you look closely at evidence, every time you wonder how something works and try to find out, you are participating in the great project that began in earnest 5 centuries ago. The revolution wasn't just about discovering that Earth orbits the Sun or that objects fall according to mathematical laws. It was about changing how humans think, how we question, how we learn. The scholars who lit the torches of the scientific revolution, Copernicus, who dared to place the sun at the center, Bacon, who charted the method, Galileo, who pointed his telescope skyward, Kepler, who found the mathematical harmonies, Descartes, who unified number and shape, Newton, who explained the apple and the moon with the same gravity. They were all driven by curiosity, by wonder, by a conviction that understanding was possible and worthwhile. Their discoveries transformed the world, but their spirit of inquiry, their courage to question what everyone believed, their willingness to follow evidence even when it led to uncomfortable conclusions, that spirit remains as relevant and as necessary as ever. As you drift into sleep, perhaps you'll dream of distant stars and microscopic worlds, of ellipses traced against the sky and blood circulating through vessels, of prisms splitting light and telescopes revealing moons. And if you found this journey through one of history's most transformative periods enlightening or restful, if these stories of human curiosity and courage helped you end your day on a thoughtful note, consider subscribing to the Sleepy Science Society. Every like and subscription helps others discover these calm explorations of how we came to understand our universe and ourselves. For now, rest well. Let your mind settle like dust motes drifting down through a beam of sunlight. The revolution continues quietly, one question at a time, one observation, one insight. And tomorrow, when you wake, you'll still be part of it. Good night.